Discover the fundamental differences between classical and quantum computers and how they process information. Classical computers use bits while quantum computers use qubits, representing fundamentally different ways of processing information. Classical computers are based on bits that store information as zeros or ones. A classical bit is like a light switch. It can only be in one of two states at any given time, 0 or 1, off or on. Classical bits are definite and deterministic. A bit is always in one state or the other, never in between. Mathematically, a bit belongs to the set containing only 0 and 1. Classical computers process information sequentially, taking inputs through logic gates to produce outputs one step at a time. Quantum computers use qubits that can exist in superposition states. A qubit can exist in a superposition, simultaneously representing both 0 and 1 until measured. Unlike classical bits, qubits can exist in multiple states simultaneously through quantum superposition. A qubit state is described as alpha times state 0 plus beta times state 1, where alpha and beta are probability amplitudes. Quantum computers can process multiple possibilities simultaneously through quantum parallelism, exponentially increasing computational power. Superposition is the key quantum property that makes quantum computers fundamentally different. Classical bits must be either 0 or 1, while quantum qubits can be both 0 and 1 simultaneously until measured. Within classical bits, you can represent 2 to the power n states, but only 1 at a time. With n qubits, you can represent all 2 to the power n states simultaneously through superposition. Quantum entanglement creates correlations impossible in classical systems. Entangled qubits become correlated so that measuring one instantly affects the other, no matter the distance between them. When qubits are entangled, measuring one immediately determines the state of the other, creating powerful correlations. A simple entangled state is 1 over square root of 2 times the sum of state 0, 0 and state 1, 1. The processing power difference becomes exponential as problems scale up. As problem size increases, classical computers scale linearly while quantum computers scale exponentially, showing massive speed advantages. Quantum computers don't replace classical computers but excel at specific problems like cryptography, optimization, and simulation. Different types of computers are suited for different applications. Classical computers excel at everyday tasks, while quantum computers target specialized problems requiring massive parallel processing. Quantum computers show promise in drug design, financial modeling, and artificial intelligence applications. Classical computers remain the best choice for general-purpose computing and everyday tasks. Quantum computers face significant technical challenges that researchers are working to overcome. Major challenges include quantum decoherence, where qubits lose their quantum properties, high error rates, and enormous costs. Qubits are incredibly fragile, requiring temperatures near absolute zero to maintain quantum states. Quantum computers operate at about 0.015 Kelvin colder than outer space. Classical and quantum computers represent fundamentally different approaches to computation. Classical computers use definite bits for sequential general-purpose computing, while quantum computers use superposition qubits for parallel specialized tasks. The future will see both classical and quantum computers working together, each handling tasks they're best suited for.